Welcome to the Short Span Steel Bridge Alliance's 2020 topic-based video series. In this series, we'll review basic concepts and ideas pertinent not only to engineers new to short span steel bridge design, but those looking for a refresher of fundamental concepts. In this video, we'll discuss the basics of construction loading and how it can affect short span steel bridge design. The goals of this video will be to provide an overview of staged loading during construction, as well as to discuss lateral flange bending, a stress phenomenon that can affect flanges in steel eye girders, as well as its sources during construction. We'll discuss staged construction, specifically the loads that a girder can experience during this process, as well as a brief overview of deck casting sequences. And finally, we'll define lateral flange bending, looking at its sources as well as relevant AASHTO provisions. Typically, when engineers first start to learn about bridge design, they're primarily concerned with the design checks for the structure in its completed state. In other words, they have a bridge, and the first and primary thought is that the girder will safely and adequately resist the loads once the structure is completed. And that is true. That is an incredibly important check for bridge design. However, the superstructure can experience different levels of stress and therefore different means of resisting those stresses during the various stages of construction. And in short span steel bridge design, it is possible that the controlling limit state for design can occur during a stage of construction instead of once the structure is completed and in its in-service state. Some loading effects to consider during the construction of a short span steel bridge. First off, the self-weight of the superstructure, namely the steel girders themselves, as well as any miscellaneous details. If there is any stay-in-place formwork, that needs to be considered, as well as obviously the wet concrete loads themselves. Also, as the deck is placed, there's going to be appurtenances applied, such as the overhang forms and brackets, the screed railing, the walkway, as well as the finishing machine. Each of these components will add stress to the non-composite girder that the non-composite girder needs to be able to adequately resist in order to generate a safe design. It is also the responsibility of the engineer to establish what's called a deck casting sequence. This is the order in which the various segments of the deck are cast in order to complete the composite deck for the bridge. In multi-span structures, it's very typical to cast the positive bending regions first, allow them to cure, and then cast the negative bending regions over the pier to complete the deck casting for the bridge. However, for most short span bridge applications, it's usually feasible to complete the deck casting in a single pour sequence. Therefore, from a designer's perspective, the non-composite steel girder would need to be strong enough to adequately resist the load effects of the wet concrete and all of the construction appurtenances during that stage of construction. Now, during the deck casting, in addition to flexure, steel eye girders can be subjected to torsion, not only in strength conditions but in service conditions as well. Now, generally, torsion can arise from a number of events. For instance, the superstructure geometry itself, such as the horizontal curvature, can induce torsion in the girder. There can also be torsional effects from wind loading and also from construction loading, which is the focus of this video. Mechanically, steel eye girders resist torsional stress primarily through warping. And warping in steel eye girder cross sections is primarily carried in the flanges in the form of a bending stress that we term lateral flange bending. When talking about short span steel bridge design, most short span steel bridges will have fairly regular geometry, and so geometry tends to not be a primary source of LFB in short span steel bridge design. Also, while wind can contribute to lateral flange bending in short span steel bridges, the girders used for short span steel bridges tend to be somewhat shallow, and so wind, while it can contribute, tends to not be as large a contributor of LFB than just the general construction loading. What happens is that the wet concrete acting on the overhang brackets, in addition to all of the construction appurtenances as shown, can generate a torsional effect in the exterior girder that produces lateral flange bending in the exterior girder flanges. Fortunately, AASHTO LRFD specifications provide some very simple plug and chug formulas for the engineer to use in computing lateral flange bending in exterior girders. The corresponding commentary in section 610 of the AASHTO LRFD specifications provide very simple plug and chug expressions for determining the lateral flange bending in an exterior girder segment as a function of whether or not you're dealing with distributed loads such as wet concrete weights or concentrated loads such as the weight of the finishing machine. Lateral flange bending moments are assumed to be uniform over the unbraced length or the distance between cross frames or diaphragms for a given unbraced segment of an exterior girder, and the moments are computed as shown. And then simply by dividing by the section modulus of the flange, we can obtain the stresses necessary for design. There are two really relevant resources that would be very beneficial to review when beginning the process of designing a short span steel bridge. First off, the Steel Bridge Design Handbook has a chapter specifically on the design for constructability. You can find that at the link shown. Also, the Short Span Steel Bridge website has a comprehensive design example of a representative short span bridge that you can find at the link on the right. And in this report, a step-by-step overview of the calculations relevant to not only lateral flange bending, but the general short span steel bridge design process are readily available. These are two really great resources for further study into the sources of lateral flange bending and a general handling of construction loading on short span steel bridges. This concludes this video on understanding construction loads. We look forward to you joining us in our next video, and with that we thank you for your time. Thank you.